So for this is the fourth video in the series of 4 videos about doing ICE charts. And in this video, I'm going to show you guys how to do a backwards ICE chart. Now, the backwards ICE chart is going to be the one that is most like your lab final. You'll have to predict how much of each starting material you're going to need. So if you read the problem below, you can see what it is. You can pause the video, try to do as much as you can before I show you the answers. I'm going to go through and show you how to do the backwards ICE chart. So much like the difficult ICE chart, in this case I gave you just names of reactants. So you're going to have to convert the names of reactants to formulas and then predict the products of the reaction based on what we know. So let's do that. So magnesium Mg2 plus, hydroxide is OH1 minus. So we need to have, let me see if I can get this thing to focus, my favorite thing. Remind me to get a better webcam at some point. Woo! There we go. Okay. So that's going to go to MgOH2. Okay, magnesium hydroxide. And of course it's not focusing. Okay. So now silver carbonate. Silver carbonate, that's Ag plus. Remember, silver is a special transition metal whose charge is only 1 plus. Carbonate is CO3 2 minus, so that's going to be Ag2CO3. Now, in order to predict the products, we're going to make our little Punnett square or tic-tac-toe board, whichever one you wish to call it. Okay, and remember, what we have is we have a pool of magnesium and hydroxide ions all floating around, and silver ions and carbonate ions floating all around. And so in a double replacement reaction like you're most familiar with, the positives are going to not attract, but the positive is going to attract the opposite negative, and the positive is going to attract the opposite negative. So in order to get this all figured out, and I do agree there's a bajillion ways to do this, but the easiest that I have found is setting this up. So you're going to start off with one reactant, Mg2 plus, and then you're going to put hydroxide here, minus, with its charge. And remember, we do not do anything with the 2 that's there. Okay, that just means you need 2 hydroxides because the Mg has a 2 plus. And so then we do the same thing with silver. Silver is a plus, and then carbonate is a 2 minus. Now, the positively charged things are not going to attract, only opposites attract, and the negatively charged things are not going to attract and form a compound. So what we have left is Ag and OH, Ag plus with an OH minus, and so those 2 charges cancel each other out, so it's AgOH, silver hydroxide, and then we have magnesium, Mg2 plus, with CO3, 2 minus. So those charges cancel out. So now we are MgCO3, 2 minus, or CO3, magnesium carbonate. Now I've taken it upon myself to already set up the ICE chart. So before I switch it, you may want to pause the video and see if you can balance the chemical equation, write the correct reaction. Here are your reactants, here are your products right here and right here, and maybe you can write a balanced chemical equation. So here is the ICE chart. It's a little long for the video screen, but that's okay. Now, what makes this different than the other ICE charts is that we are trying to make a certain quantity of the magnesium containing product. So the problem says start with, or we want to make 7.43 grams of this product at the end. We want to finish with that amount. So That's fine. So when we get into the lab, we want to make sure that this is how much is on our filter paper, this is how much we put in the oven, this is how much ends up on the balance. But that's our end box. This is why this is a backwards ICE chart, because what we're going to do is we're going to start here and work our way and go up to these values, as opposed to starting with these values and work our way down to the end. That's why this is a backwards ICE chart. So you've noticed on here that I've already put the molar masses up here, and so that's going to help us out. And so to use this, we're going to go from grams to moles. Remember, in the lab, we always have grams. This is what we measure in the lab. But we don't have mole meters in the lab, so we don't do things in moles in the lab. But when we do it on paper, we have to use moles. So we have to convert this value to moles here. That's going to start us. So we're going to go 7.43 grams of magnesium carbonate. We're going to X-line it, and we're going to put grams on the bottom, moles on the top. Okay, and 1 mole weighs 84.3 grams. And so when we do that math, we get 0.0881 moles of magnesium carbonate. Now, it's my opinion that this is a little bit easier than traditional ICE charts, and I'll show you why in a minute. So now we put 0.0881 moles in here. Now, this is one reason why it's easier. Whenever you have a double replacement reaction, up until this point, we've had to try to figure out the limiting reactant, and then that adds a whole bunch of stuff in here. Now in this case, because we're going backwards, well, how much product do we always start with? We always start with 0 products. 0 products. I guess I should make my 0 a little better. Okay. Because what would be the point of doing a chemical reaction if we already had the products that we're trying to make? So that means that this change box is going to be 0.0881 moles. Now we have done a double replacement reaction now, and we didn't have to do a limiting reactant calculation. So that makes this a little easier. So now, just like every other ICE chart, the first change box is always the most important. So we're going to use that change box to calculate that, and just for completeness, because I don't want to leave any stone unturned, we're going to do this. Now, notice we can use a shortcut here. This is a 1-to-1 ratio. So for every 1 mole of these, we're going to we're going to use 1 mole of those. I'm sorry, this should be plus 0.0881. Okay, but for every 1 mole of these that we make, we're going to use up 1 mole of this. So if this were 2, this would be 2. If this were 18, this would be 18. So because this is 0.0881, this is going to be minus 0.0881. And now, if you notice, hopefully, in your reaction, you'll notice that this also has a 1-to-1 ratio for the same reasons that this then is 0.0881. This is 0.0881. Now, again, we don't need it in this case because we're just trying to get up to here, but I will add it for completeness. To go from here to here, it's a 1-to-2 ratio, so we would have to X-line it using the balanced chemical equation. That's a 1-to-2, so this is going to be twice as much, so it's going to be plus 0.176 moles. Now, 0 plus 0.176 equals 0.176. Now, this is what makes this so super easy, is that when we're doing chemistry, we want to conserve as much of the reactants as possible. So how much reactants do we want here at the end? Well, 0. How much of this do we want here at the end? 0, because we don't want to have any leftover stuff that we have to try to separate from here. We're already going to have some here. So if we try to make these two values 0, that means that everything's going to turn out all fine and dandy and we should be okay. So because this is another reason why this ICE chart becomes easier. So now how much do we have up here initially? Well, the only way to get to 0 is to start with 0.0881 moles. The only way, again, to get to 0 here is to start with 0.881 moles. Now we can spend a little bit of time and convert these to grams. I am not going to show you how to do this, but you're more than welcome to pause the video and see if you can do this. But when we do this, okay, I'll even give you a second here because I'll show you this. I converted this. This is 22.0 grams. Now when I converted these two numbers to grams using the X line, this one became 5.14 grams, and this one became 24.3 grams. Now, the last thing that we should always do is just check using the law of conservation of mass. If we add these two, you get 29.44 grams, and if you add these two, you get 29.43 grams. Look, these two are almost exactly right. So what does this mean? When we get to the lab and we want to figure out how much reactants to start with, we're going to add 5.14 grams of magnesium hydroxide to 24.3 grams of silver carbonate, and that should yield us 7.43 grams of our desired magnesium compound.